Thevenin's theorem is a valuable and useful tool. We'll use it this week, and we'll use it again next week. So it definitely has a couple impedance matching calculations and stuff. Thevenin's theorem comes in handy. So all it's saying is that you can replace, if you have a circuit like what we've shown here, with a source and a series of resistances, from the perspective of the terminals A and B, this can be replaced with a Thevenin voltage and an equivalent Thevenin resistance, as seen from the terminals. So in other words, if you're from the load's perspective, in this case, we're going to attach some load between A and B. From the load's perspective, these sources and associated resistances can be combined into a single Thevenin voltage and a single Thevenin resistance. And to the source it looks the same, or to the load resistance it looks the same. Any linear circuit can be done this way. Some uses: maximum power transfer occurs when Thevenin resistance is equal to load resistance. And for AC circuits, maximum power transfer occurs when the load impedance is the complex conjugate of the Thevenin equivalent impedance. So if you get a Thevenin impedance of X plus JY, then the maximum power transfer occurs when the load impedance is X minus JY, or the conjugate of the Thevenin impedance. So how do we get there? Well, we remove or open the element of interest. So basically, you think of snipping the circuit at the terminals, and then calculate the Thevenin voltage with voltage sources shorted and current sources opened. And we'll do Thevenin voltage by using Kirchhoff's current law, voltage law, and/or Ohm's law, sometimes a combination. And then we'll calculate the current flowing through the element of interest. So let's see how that works. Here's some equivalent circuits, by the way. You can do this by measurement as well. Take a voltage measurement. That'll give you your Thevenin voltage. And then you can look at what they're talking about when they short. You're shorting the sources and stuff to find the Thevenin impedance, or the Thevenin resistance. But that can also be measured, by the way, to build your equivalent model. Let's take a look at an example. So suppose we have this circuit here, 50 volts, 20 volts, a couple of resistances in here, and it says find the Thevenin equivalent voltage and resistance as seen by the 10 ohm resistor. So we're considering the 10 ohm resistor to be the load resistance. So we're going to, the best way to think of this is consider the Thevenin equivalent circuit. So this would be like your A and your B nodes here. You're basically looking back in, if you pulled these out and basically looked back in to try and find voltage and resistance, that would be your Thevenin voltage and your Thevenin resistance.